Hi, welcome back to Civil Engineering 305. Today we are interested in looking at stresses, and actually we are going to look at something fairly important for our class, which is the following task. Our task is given a stress state and a failure criteria or let me write it in a different way, and a safety criterion to figure out whether the structure is safe at that point and some idea of how it is likely to fail. So two things, right? So first I'm interested in I'm given a stress state. We will talk about what this means. And I'm given a safety criterion, which tells me what kind of material it is and how it is likely to fail. Based on these two things, I want to figure out whether the structure is safe at that point, whichever point on which I know the stress state, and some idea of how it is likely to fail. Is it going to fail sideways? Is it going to fail, which way is the crack going to grow, if there's going to be a crack, or is it going to slide off, or what's going to happen? Okay, so the idea is, first thing is definition, stress state. This is a listing of stress components on three perpendicular faces. Notice, up to now we have only been talking about two perpendicular faces, but we did some examples when we looked at this idea of what is meant by stress components, right? Sigma ij, remember face the force. So now we are really looking at listing of stress components on three perpendicular faces. What do I mean? So I'm going to draw a nice picture, and we're going to see if we can actually figure it out. So first I have some body, so let's draw this thing. So here's the body, okay, and you have applied some forces to it. You're doing horrible things to this body, pulling it, pushing it, sliding it, whatever. Know what I mean? And what happens is, somehow or the other, if I look at a little chunk here, that piece of this body, I know what are the stress components on this chunk. We will explain what I mean by that. Okay. So how would you find out the stress component of this chunk? We don't care. This is what, so maybe you have done a very complex finite element analysis or something like that, or you figured it out some basic ideas like what we did for seams and welds and things like that. Some simple way of figuring it out. So once I have that, the question is what happens. So let us look at a particular example. So I am given. So let's first look at the listing of the stresses. Okay, so here is the face. First thing I do is I'm going to assign some stuff. So this will be called x component, y component, z, and then we know all these things, right? So we already know that this will be called sigma zz. This will be called sigma xx, this will be called sigma yy. You can see face the force, right? Y face, y force, z face, z force, x face, x force. That's three. What are the other three things? I need to specify the shear stresses. So the shear stresses, I'm going to do it in a different color so we can see it. Let's do it in the ballpoint pen. Yeah, there you go. So shear stress this way. what will it be called? It will be called sigma y phase z force. This way, sigma y phase x force. Then this way, sigma x phase z force. Right? How about this one? Sigma x phase y force. These two things are equal. Okay? Remember, torque, balance of angular momentum will make sure that those two things are equal. How about this phase? If you look at this phase, sigma z phase x force and the sigma x phase z force are the same. Sigma z phase y force and sigma y phase z force are the same. So I need 6 numbers. What are they? So this is very, very important. So if I list these things, sigma xx, and I'm going to write it in a matrix version. Sigma xy, sigma xz, sigma yy, sigma yz, sigma zz. These 6 numbers, of course these things are symmetric, so I don't really need to list them separately, but I'm going to do that anyway. So these things are symmetric, so I got sigma yx, sigma zx, sigma zy. Okay, this matrix, these 6 numbers, this is what we mean by the state of stress or the stress state. In particular, for most of the examples that we are looking at, all these things are 0. So sigma xz is 0, sigma yz is 0, sigma zz is 0. So of course these 3 things are gone. And now I will have only a 2-dimensional state. You can see that, right? That is called plane stress. What does plane stress look like? If I draw a cube, and then I start marking the points. So this is the x phase, sigma xx is there, sigma xy is there, then sigma yy is there. Sorry, xy is not vertical, I'm sorry, so I got to draw this right. Let me do it right, okay? So this is sigma xy, and this is sigma yy, and this is sigma yx. And the z-axis is like that. Notice this whole plane, no forces on this plane. That's why it is called plane stress. There is one plane on which there are absolutely no forces. If you have a situation like that, you have plane stress. For example, if I am taking our usual plate of steel or something like that and I am pulling it, can you see there's one face on which there is no force? That's this face, right? I'm not applying any forces to this place. So if I take a small piece of material here, it will be like this. And in fact, that's what we are talking about. So let's define plane stress equals no forces on one plane.